Hello. This lecture will cover pages 60 through 67 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Describing Logic Circuits, Part E, the NOR and NAND gates. Going to start out on page number 60. We're going to look at the NOR gate. Now keep in mind we looked at three gates so far. We looked at the inverter, we looked at the OR gate, and we looked at an AND gate. Now we're going to look at the fourth gate called a NOR gate. The two symbols for the NOR gate looks like this. Notice it's an OR gate with a bubble at the end of it, and if the truth table for it is off here to the right. I don't want you to memorize truth tables. Remember that. I just want you to memorize logic symbols. I'll show you what I mean by that in just a minute. The other way of drawing this gate is, remember the basic rule I told you. The basic gate is an OR gate. You change the basic gate to an AND gate. You invert the inputs. This is a high true input, a high true input. You make them low true inputs, and you invert the output. That bursts a bubble. These gates are the same gate. They are both NOR gates. Let's see how this tells the story. A high here or a high here is the only time you get a low here. A high here or a high here is the only time you get a low on the output. So the story is told as a 0, 0, 0, and by default there's a 1 there. Down here, a low here and a low here is the only time you get a high here. That story is told here. A low here or a low here and a low here is the only time you get a high here. By default, these are zeros. Notice the truth tables are identical. If the truth tables are identical, the circuit's identical. Sometimes the engineer will draw it this way. Sometimes the engineer will draw it this way. We'll explain why a little bit later on. The 7402 quad 2-input NOR gate package is the IC that holds the NOR gates. And if you take a look in your specifications on page number 274, this is what you'll see here. Notice we're looking at a quad 2-input NOR gates. There's 4 of them in the package. Pin 1, let's see where we're at here with pin 1. Here's pin 1 is an output. Pin 2 and pin 3 are inputs to the first gate. Pin 4 is an output. Pin 5 and pin 6 are inputs to the second gate. Pin 7 is ground. Pin 14 is VCC up here. And notice we have the inputs 8 and 9 for the third gate. Output is 10. 11 and 12 are inputs to the fourth NOR gate, and the output is 13. That's the IC package we'll be using in lab. It's called a 7402 IC package. If you take a look at the bottom of page 60 here, this is an example. I think you have this for homework. Don't forget the gate can be drawn like this, or it can be drawn like this, depending on how the engineer wants to tell the story. And to illustrate what I mean by that is, let's take a look at, this is an A input waveform, this is a B digital input. This output, X here, whenever you get a 1 here or a 1 here, that's the only time this is going to be low. So a 1 here or a 1 here. A 1 in either case, this will be low. So notice it's low from this point to this point, it's low because of pin A. Okay, and from this point forward, pin B, or input B and input A are both high, and that's keeping it low. Notice that B input goes low, but as long as A or B is high, the output stays low. And it does up to this point. At this point here in time, notice both A and B inputs are low, so the output goes high. At this point in time, B input goes high, the output goes low. It stays low the whole way out to here. That's when both of them are both low again. They go high. You should be able to reproduce this waveform, but you can also reproduce this output waveform by this gate. This gate says a low here and a low here is the only time you get a high. Well, the only time you're going to get a high is when they're both low. You get the same output waveform no matter what gate you use. They tell two different stories, though, but they implement the logic identically. Make sure you understand that. The NOR gate is very important. However, the most important gate we're going to discuss, the fifth gate, by far it's the most important gate. This is the one you have to know the most about in this class. It's called the NAND gate. It's the universal building block. Why? Because the NAND gate can be used to build any other gate or logic circuit. Any digital logic circuit you can build by simply using NAND gates. When we were at Texas Instruments, we had to use hundreds of thousands of different types of NAND gates. We had to use a lot of OR, a lot of NAND, a lot of inverters, a lot of OR gates, a lot of NOR gates. But what we would do is just buy a couple 100,000 NAND gate packages, because we could build any gate we want by using the NAND gate. And I'm going to show you how you do that very shortly. The two different symbols are here and here. Sometimes NAND gates shown like this, drawn like this. Sometimes the NAND gate's drawn like this. How do you get this symbol? The basic gate is an AND. You invert it to, you change it to the OR. You invert the inputs and you invert the output. These gates, this is the same gate. Look at the truth table. A 1 here and a 1 here is the only time you get a low. A 1 and a 1 is the only time you get a low. All other times it's high. Down here it says a low or a low is the only time you get a high. A low or a low is the only time you get a high. By default, it goes to 0 here on 1, 1. These are identical. The truth tables are identical. When the truth tables are identical, the gates are the same. It comes in a 7400 quad 2-input NAND gate package. You can see page 95 in your book or in your specifications here. You can take a look at what it looks like here. Similar to the 7402 quad 2-input or NOR gate, but the 7400 is a quad 2-input NAND gate. 4 of them in the package. You'll be using this in lab a lot. This is on page 273 of your specifications. On page number 62, notice this is your homework. You have a homework that looks like this. You have an A and a B input, and you want to find out what the output is. I don't know if you have this in your lecture notes like this, but make sure, based on these two inputs, you can reproduce that X output. This says a 1 here and a 1 here is the only time you get a low. You have to have a 1 on A and a 1 on B. It's the only time you get a low. So you draw your lows in, the rest of the time it's high. Or you can use this gate up here. It's the same gate. That's a NAND gate. It says a low or a low is the only time you get a high. Anytime there's a low on either one of these lines, A or B, that's when you get a high here. I don't care which one of the gates you use, you get the same X output waveform. Universality of the NAND gate. Very, very universal gate, which means you can make any other gate from it. Show you what I mean. We want to build an inverter in a circuit. How can we use a NAND gate to build an inverter? Well, you just tie the two inputs together. You tie the two inputs together. Let me show you what that does for you here. First of all, let's look at the NAND gate truth table here. Let's say we have an input A, B, your output Y. I don't memorize truth tables. I write everything in order here. 0, 0, 0, 1, 1, 0, 1, 1. If you take a look at what the gate looks like here, the NAND gate looks like this in its basic form. This is Y, here's your A, and here's your B. This says a 1 here and a 1 here is the only time you get a low out. That's where the story's told. By default, this is 1, 1, 1, and that is the truth table to the NAND gate. Well, what happens if we tie these two inputs together and we just make it one input? Let's just call it A. Let's just call the input A. Or just get rid of B now. We just have A. One input goes to both of those. Well, as soon as we tie them together, we can't have this situation because A and B is different. And we can't have this situation. How can A be at 5 volts and B be at ground? Or how can A be at ground and B be at 5 volts? These can't happen. You either have the input being 0, and you get an output as a 1, or you have the input as a 1, and the output goes to 0. That's an inverter. That's a way of drawing an inverter. If you don't have any 7404 packages handy, use the 7400 package, take one of the NAND gates, and build an inverter out of it. If you take a look down here, how do you make a NAND gate? How do you make an AND gate out of NAND gates? Well, that's pretty easy. There's your NAND gate. And we want to make a NAND gate, an AND gate out of that. Well, we just have to put an inverter out here. If you put an inverter out here, that circuit just becomes, that circuit here, just becomes an AND gate. Well, you know how to put an inverter in. We did it in the last problem. Put another NAND gate in. Tie the inputs together. There's your NAND gate. There's your other NAND gate with the inputs tied together. It's an inverter. That part of the circuit there is equivalent to an AND gate. And finally, what about an OR gate? How do you make an OR gate from NAND gates? You ought to try that, but don't get hung up in the logic. It's so much easier just to think about this a little bit. I mean, basically, you have a NAND gate. And you want to make an OR gate. How are you going to make an OR gate out of that? Well, remember the other form for this gate. You change the basic gate from an AND to an OR. You invert the inputs, and you invert the output. We're almost there. There's an OR gate. Let's move these bubbles away. Let's move these bubbles out here. They're inverters, by the way. You can do that when you're writing on paper. Just inverter there and inverter there. You put 2 NAND gates on the input. Make them inverters. So basically all you do is, let me erase this. Let me erase the top one. We'll keep this look there. Oops. Sorry about that. Oh, classroom lecture is so much easier than this. Anyhow, there we have an inverter. There we have another inverter. Okay. And you run that into another NAND gate. A NAND gate, a NAND gate, and a NAND gate. There's 3 NAND gates, and those 3 NAND gates make up an OR gate. How does it do that? Well, this bubble, this inversion gets rid of that bubble. This inversion gets rid of that bubble. So you basically have an OR gate. That is an OR gate using 3 NAND gates. 3/4 of a 7400 package. On page 63, the last gate we want to mention for a while is the buffer gate. The buffer gate is basically a gate that just passes the signal through, but it isolates it. The symbols look like this. It looks like an inverter with no bubbles on it. You put in truth tables, you put in a 0, you get out a 0. You put in a 1, you get out a 1. And you can draw it this way, you can draw it this way. Either way, Depends on how you're telling the story. It's used for isolation or fan out, which we'll talk about coming up within the next week or two. If we're going to run the signal, you can't run these outputs to 100 places, 200 places with some of these IC families. The fan out is how many places you can take the output to other places in the circuit. You'll find out that some of them are limited to 10. Some of them are limited to 20. Some of them you can take 1,000 in different the outputs to 1,000 different inputs. But you have to be able to isolate the outputs, and that's what the buffer gate does. And we'll talk about that later on. Review of the gates. So far, we've talked about the first gate was the inverter. The second gate was the OR gate. The third gate was the AND. The fourth gate was the NOR. The most important gate, it was the fifth gate, which was the NAND gate. Make sure you study that carefully. And then 6 was the buffer gate. On page number 64, we've already discussed why we use Boolean algebra. Page 65 and 66, I want you to go ahead and work those simplifications. If you look on page number 65, this is the reduction of that circuit. How many gates does that, look at that equation. From that equation, can you see it takes 1, 2, 3, 4, 5, 6 gates. There are 6 gates needed. But not really. Notice we have B inverted, and we have B inverted, so I could just run this inverted B signal. This is B inverted right here. I could just run it down to here and get rid of that inverter. I don't need to invert it to run this signal separately like that. So 5 gates. 5 gates to build that logic circuit. I just look at the equation and I say, well, here's a 3-input AND gate. That's 1. Here's a 3-input AND gate, that's 2. Here's an output gate, which is 3. And I need a B inversion and a C inversion, that's 4, 5. 5 gates from looking at that. You can look here, you can look there. Down here, what about this example? How many gates does it take to implement this expression here? Make sure you try this on your own. You might want to stop the video and run through this, but basically, how many gates does it take here? Well, it takes 1 3-input AND, another 3-input AND, and an output OR. That's 3 gates. 1, 2, 3 gates, and then we have to invert B, and we have to invert C. That's 4, 5 gates again. It takes 5 gates. But if we reduce that using the Boolean algebra techniques, here's the distributive law, 13A and 8 and 2, and we can reduce this down to just A and B barred. Here, that's 2 gates. We went from 5 gates to 2 gates. This is the way we'd implement the circuit. And then if you look at page number 65, this takes 4 gates to implement. You run through the reduction. You don't need any gates. It's just a wire. Here's the reduction of this. In this example right here, it takes 4 gates to implement this. You go through the reduction, you get down to 3 gates. So you save yourself a gate by running through the reduction. Same thing down here. Go through each one of these examples. Make sure you can do each of these individually. Here's the answers for it. And that concludes the lecture.